We're going to be learning about three basic types of symmetry. Symmetry with respect to the x-axis, symmetry with respect to the y-axis, and symmetry with respect to the origin. And I have two different examples. One that will illustrate the x and y symmetries, and then I have another one that will hopefully demonstrate the respect to the origin symmetry. So for my first example, I have y is equal to x squared, and you may have already graphed something like this and noticed some symmetry. So we'll put a graph of this up. And the graph of these kinds of equations, I'm not going to actually use points, I'm just going to kind of draw the basic idea of what it looks like. It looks like this. I'm trying to be as symmetrical as possible, but you can see the drawing's a little bit off, but you get the general idea. You can see that this side is the same as this side when we divide it down the middle here, and this, so this is the y-axis. So we can say that this graph is symmetrical with respect to the y-axis. And if we had this sort of thing except pointed this way, it would be symmetrical with the x-axis. So actually, let me draw a really small graph. Actually, I'll worry about that later. Let's just worry about this. Let's just worry about this one for now. So we say that this is symmetrical with respect to the y-axis, not the x-axis. Because if we were to put a mirror right here, it would reflect to the other side. That is what the definition of symmetry is. So now that we know where the symmetry is, it's symmetrical with respect to the y-axis, let's try to see if we can identify what's causing the symmetry. So the reason that there is symmetry is because this side is the same as this side. But what is causing it? We have our positive x values are equaling the same y. So here we're going negative, or we're going x 1, 2, 1x, 2x, 3x, 4x. And here, in this direction, we're going minus 1x, minus 2x, minus 3x, minus 4x, etc. But the thing is that both of these x's, so if I put in 1x, it's giving me 1. So let's say y is equal to 1 squared, which is equal to 1. So I got 1, 1. And if I put in minus 1, minus 1 squared is equal to 1, so I get minus 1, 1. And we can do the same thing for 2. We can see that we're going to continue to get the same number no matter what number we put in, no matter what pair of what numbers we put in. So for like 2 and minus 2, 3 and minus 3, 4 and minus 4, they're going to be equal because we're squaring it. And that is what is causing the symmetry. The fact that if for whatever x I put in, positive or minus, it will give me the same answer. As long as it's the same numerically, it's like minus 1 and 1, 2 and minus 2, 3 and minus 3. So now I'm going to show you the test. Now you can understand what the test actually means. So in order to test for symmetry, what we're going to do is we're going to plug in the equation with x and minus x. And if we plug these into this equation and they give us the same thing, that means it's symmetrical with respect to the y-axis. Because if we put in the same numbers except just plus or minus, and they give us the same exact y, that means it's symmetrical. That's what we just spent all this time talking about in this graph over here, the fact that the y's are the same. And we'll see how that mirrors the the x-axis, where we're going to get the same x values. But let's just talk about this example for now. So obviously we already have in just positive x for this equation, so we never really need to do this one because it's already given it to us like that. So we just plug in minus x now for this test. So minus x squared, and we just do the algebra, and that's very simple, and we get y is equal to x squared. So we get the same exact equation whether we put in positive x or minus x. So if we get the same equation again, so here we just put in minus x, we got this equation, and that's the same as the original one. So that means this is symmetrical with the y-axis, because if we put in the same x's, if we put in the positive and minus x of the same thing, and we get the same answer, that means it's symmetrical on the y-axis. See, look, x's getting the same answers. That's what causes the symmetry. Now let's talk about symmetry with respect to the x-axis, not the y-axis. So if I was to turn this graph sideways like this, so let me just kind of draw something like this. So if it was going sideways like this, this would not be symmetrical with the y-axis. So if I cut it down the middle right here, it wouldn't be symmetrical. But if I cut it in half going this way, it would be symmetrical. So it would be symmetrical with respect to the x-axis. And it's very similar to sort of finding the way we find symmetry for the y-axis, as you'll see. The only difference is, in this case, the y's aren't the same. See, here we have y that's, kind of increasing for different values. But what's happening is that the y values in this case, so we have the positive y and the minus y, are giving the same x values. So if we had 1y, it would give us the same x value over here. It's the same thing, but except you switch the y, except the role of the y and the x has been reversed. So it might be a little bit stranger thinking about it in this direction, because normally we think about plugging in x's and getting y's rather than plugging in y's and getting in x's, but it works the same way. It's just sideways, so it looks strange. But this operates on the same idea. So in order to test for symmetry with respect to the x-axis, instead of replacing instead of replacing positive x with minus x, we replace positive y with minus y. So if we get the same thing for y and minus y in our original equation, then it is symmetrical with the x-axis. But we already know that it's not going to be. See, this is our equation right here. This is just an example, this dotted line. So this is a sort of hypothetical. If it was that way, it's not. But I was just using that as an example to show you how you would think about testing for symmetry with respect to the x-axis. So let's do this. Let's find out if this is symmetrical with the x-axis. So to find out if it's symmetrical with the x-axis, let me rewrite the equation. Y is equal to x squared. So for the first time, we did respect to the y-axis, and by doing that, we replaced in x with negative x, and we got the same equation. But to test for symmetry with respect to the x-axis, we replace y with negative y. So let's do that. So we have minus y is equal to x squared, which gives us, so if we solve for y, y is equal to minus x squared. And this is not the same as this. So it is not symmetrical. So it's not symmetrical with y, or with the x-axis, sorry. And that's the other thing, you have to be very careful not to mix up the axes. In order to test for, let me write this out real simple. So for symmetry with the y-axis, we replace x with minus x. And if they're equal, then it is symmetrical. And if they're not equal, if you do not get the same equation, then it is not symmetrical. And for symmetry with the, let me get a brighter one. And for symmetry with the x-axis, we have to replace y with minus y. And if they are the same equation, then it is symmetrical, and if they're not the same equation, then it's not. So again, let's go over this example real quick. In this one we replace, so for this one, let me write it down here. So for y is equal to x squared, we found out that we replaced minus x with x, or we replaced x, we replaced x with minus x, and we got the same thing. So it was equal, it was the same equation, so it was fine. So it was symmetrical. Symmetrical with the y-axis. And then we replaced y with minus y, and we got y is equal to minus x squared, which is not equal to this. So that's all there is to it. You just replace the appropriate axes with a minus of whatever it is you're looking for, and if you get the same thing, it is symmetrical, and if you don't, then it's not. So now that we know how to test for symmetry between x and y axes, let's figure out how we would test for symmetry with respect to the origin. So I have this equation, y is equal to 1 over x, and I'm going to graph it. It's kind of an off graph, but oh well. And this equation goes like this. The graph goes like this. I'm not going to actually graph points, but I'm just going to show you how the graph of this would go. And this is kind of a crappy graph, but you can see again what the basic idea of it is. These two are going to be exactly the same, but here we can see if we divide it down the middle, there's no symmetry with respect to the y-axis. So if I was to put a mirror here on either side, it would reflect it over here. For on this bottom half, and on this top half, it would reflect it over here. So there is no symmetry with respect to the y-axis. And the x-axis, again, there is no symmetry either. It's just sideways. Instead of a mirror reflecting this over here, a mirror would reflect this over here, and a mirror would reflect this over here. So there is no symmetry with respect to the x-axis. But there is symmetry along a diagonal line, like here. So if I was to put a mirror diagonally here, this would reflect over here, and that is symmetrical. So we understood what was causing the symmetry for the x and y symmetries. What was causing the symmetry was the fact so let's scroll up again. What was causing the symmetry with respect to the y-axis is that whenever you put in an x and a corresponding negative x, you would get the same answer. And for here, if you would get the same y. And with respect to the x-axis, if we put in a y and a corresponding negative y, we would get the same x. Here we're not getting that. Here what is happening is, if you notice, here let's try to think about it like this. Here, x is positive and y is positive. Here, x is negative and y is negative. So we can have, well, with respect to the origin, there are two ways we can have our symmetry. We can have it going this way, but also let's say if this graph was going this way instead, we could also have symmetry going this way. Just so happens that this equation I picked, this graph looks like this, but if, let's say if it was, this was up here and then this was down here, we would still have this sort of symmetry with respect to the origin. It would just be on opposite sides. But on here, but let's say if that did happen, here we have minus x's, positive y's, and then here we have positive x and minus y. So if we notice, it's a simple changing of the sign. So here we can have symmetry and here we can have symmetry, and all that's happening is that x and y are having, basically, they're being multiplied by -1. Their signs are being switched. So again, we're noticing a switching of the signs that are giving us the same numerical answers. And the test for symmetry with respect to the origin is that you replace both x and y with minus x and minus y, and you get the same answer, or you get the opposite of it. Or let me just show you. It'll be much easier to get. It's a little bit confusing. So we replace this with y with minus y. We go over here and replace x with minus x, and that gives us minus y is equal to minus 1 over x. But if we multiply, which say, hey, hang on, it's different, but the only thing is you have to notice that both sides are being multiplied by -1, so it's the same thing. If both sides are being multiplied by 2, we could divide out by 2, and it would be the same thing. So we can multiply both sides by -1, and we get the same equation, y is equal to 1 over x. So this is how you test for symmetry with respect to the origin. Now that we know the test for the origin, let's go back and test our first example, which we know is not symmetrical with respect to the origin. So if we replace y with -1, or minus y, doesn't matter, multiply by -1, and x with minus x squared, we get minus y is equal to x squared. And this is not equal to this. So it is not symmetrical with respect to the origin. There we go. So those are the simple tests. Again, let's just go over real quick. So with respect to the y-axis, we replace x with minus x. For respect to the x-axis, replace y with minus y. And for the origin, replace x and y with minus x minus y. And the only one you really have to be careful with sometimes is just with the origin. Because like I explained earlier, in this example, we got minus y and minus x, but again, we could multiply it by -1, which gives us the answer. So you kind of have to just keep an eye out for something like that, where sort of on the surface it might appear to be different, but you're multiplying both sides by -1. So you can which makes them still equal, because you can multiply both sides of the equation by -1 and you get back the original equation. Whether in the other ones you would not be able to do that. So these are all the tests for origin. You might want to still continue to graph the equations, or at least put it into a graphing tool, whether a computer or a calculator, and see the origin. That's the thing about these ones. You can always check to see if you got it right by putting it into a calculator or some other graphing tool, and you can see and you can check your answers by just visually looking for symmetry.